So, the first one to go on and present the results will be Peter Witz from Aachen. Please come on board, Peter. You see here.
Hello everyone, can you hear me? Perfect. So welcome also from my side. My name is Peter. I'm a research associate at the RWTH Aachen University. And the topic of my presentation today is hydropower in the European energy system. What are the future flexibility requirements? Therefore, I would first like to show the role from RWTH within the HydroFlex project. And the RWTH is the leader of the work package 2, as Ola said already. And we focus on the flexibility provision by hydropower from a power system perspective and on future operational requirements for hydropower. We have a few tasks. The first task, to define 3 European energy scenarios, was done very early in the project. And based on this defined scenarios, we did a lot of calculations and simulations and summed everything up in a guide describing future operational requirements of hydropower. Today I would like to show some main results and key driver for flexibility demand, which we also described in our guide and is online on the website. So our simulations and investigations are separate into 2 parts, a market simulation part and a time domain simulation part. And in the market simulations, we focused on the day-ahead market and the intraday market, so the time before the physical fulfillment. And in the time domain simulations, we simulated a fault occurrence and focused there on inertia and frequency containment reserve. First, I would like to start with the market simulations. This simulation model is divided into 2 steps, so it's a 2-step approach. The first step, there we used a European market simulation, and the second process step, we developed a hydraulic unit commitment model. As a result from these simulations, we get the detailed feed-in time series of the hydropower plants. I would like to go a little bit more in detail of the overview for the market simulations. You see in the second and the fourth column the 2 steps, and the input data for the first step, the market simulation, are power plants, net transfer capacity, rest time series, primary energy prices, demand time series, and bidding zones. And we derived this from the predefined scenarios which I talked about before. The objective of the market simulations are to minimize the cost of generation. The hydropower is in this simulation viewed in aggregated form because of the high complexity of the European power system and the modeling of these. Furthermore, also due to the high complexity, we considered hourly time resolution in this market simulation step, and as a result we get feed-in time series, power exchanges and reservoir levels, etc. So then we use the results from the market simulation, the aggregated feed-in time series of the hydropower plants per bidding zone, as an input data for our second process step, the hydropower plant commitment model, which is a rule-based algorithm, and the objective of this model is the efficient use of available water considering technical restrictions. In this step, we considered all hydropower plants in the Nordics more in detail and considered a time resolution which is quarter hourly. As a result, we get this quarter-hourly detailed feed-in time series of every single hydropower plant in the Nordics. Next, I would like to describe a little bit more the investigation plan of our market simulations. On the left side, you see the spatial scope of the two steps, the market simulation. In the market simulation, the spatial scope is the European area, where we aggregated the hydropower in the Nordics due to its high complexity. And in the second step, we only looked at the Scandinavian countries, Norway and Sweden, where we also divided Norway into two bidding zones, Norway and Norway South. In this step, the hydropower are now viewed in detail and not in aggregated form. As I said in the beginning, we defined 3 different energy scenarios, which are now the input data for our investigations. We defined a green hydro scenario, a reference scenario, and a prosumer scenario for the year 2030 and for the year 2040. When we take the reference scenario for the year 2030 as a reference for the others, they are the main differences between the scenarios are in the installed capacities of the PV units and the wind turbines. So as you see in this chart here, the installed capacity of PV units increases both in the green hydro scenario and the prosumer scenario, whereas we see even further increases of wind turbine installed capacity in the green hydro scenario in 2030. When we look from the year 2030 to 2040, we see that both installed capacities of PV units and wind turbines will increase in all scenarios. On the right side, you can see the number of power plants we are looking at in the Nordics, which are, to sum it up, 426 units we are looking at, and this is about 41.4 gigawatts of installed capacity. But we assumed in our investigations to only consider hydraulic storage power plants above 10 megawatts, which results in about 9 gigawatts in Norway, 20 gigawatts in Norway South, and 12.4 gigawatts in Sweden. So now we would like to answer the question, how will Nordic hydropower as part of the European power system be operated in the future? And therefore, we compared the number of operating point adjustments above 100 megawatt from the aggregated market simulations results. So we look at the time series and see how often does the power changes are above 100 megawatts in this time series. And we compared all the aggregated feed-in time series for all scenarios and bidding zones that you can see on the right side. And it is noticeable that the number of operating point adjustments above 100 megawatt is always between about 700 and 1,100 per year and differs only slightly between the scenarios. This results in about 2 to 3 operating point adjustments per day in each market area. So the number of operating point adjustments is also highest in bidding zones and scenarios with a comparatively high share of wind turbines, as we see at the green hydro scenario or Norway or in Sweden. And now we are asking, the question arises, what is the reason for the only slight increase in flexibility demand in these future scenarios? And therefore I would like to show some time series of PV feed-in in Germany, the hydropower feed-in in Norway, and the net exchanges in Norway South for one exemplary scenario and about 2 weeks, you can see here. And as you can see, the electricity generation from the PV units from Germany has a significant influence on the hydropower operation in the Nordics. So this is the reason why we only get frequently one start-stop cycle per day in most of the units. Furthermore, you see that the exchange capacities are usually completely used due to the high price spreads between the bidding zones from Central Europe to the Nordics. So what we see is that there are often no further demand for flexibility through the exchanges to Germany. And this was the question, what influences the results from other bidding zones, which are neighbors to Norway and Sweden. Therefore, you can see on the right side the annual duration curves and of the net exchanges for the neighboring countries. And what you see here is that the transmission capacities between Norway South and Germany, the UK, the Netherlands, and Denmark West show a similar utilization rate. So you see on this slide that about 10 months of this annual duration curve is fully utilized. So only a few time slots are left where flexibility demand can come from. And this is the result because of the often high price spread between Nordics and Central Europe. But what we can also see is that the transmission capacities between Norway South and Norway and Sweden, so in the Nordic region itself, are frequently not fully utilized due to the more similar power plant park and significantly smaller price spreads between these bidding zones. So we see that higher flexibility demands are more likely to be expected from the Nordic region itself than from Central Europe. Then what I said in the beginning is that we see a slightly increase in the flexibility demand in scenarios with increased wind capacity. So to trigger this one, we did a sensitivity analysis where we even increased the highest wind capacity from the green hydro scenario 2040 from 10.4 gigawatt to an increased capacity of 28 gigawatt to see the differences this would make in the future. And there we see that the increase of start-stop cycles in Norway itself, where we increased the wind capacity, increases significantly in this one. But there are hardly any changes in Norway South and Sweden itself due to the greater influence of the power generation from PV units in Central Europe. So what we see that higher shares of wind in the Nordics are a main driver for higher flexibility demand, as long as the influence from power generation from PV units is only moderate. Next, we analyzed what could be additional benefits for a flexibilization of some turbines, and therefore we did one simulation without any flexibilization and one where we flexibilized the reference sites which we defined in the framework of the HydroFlex project. And there on the left side you can see the number of operational violations of the minimum operating time and minimum downtime. And there you see that these can be reduced by 66% when we flexibilize the reference sites in the Nordics. And also on the right side you see that the inflexible plants show a little bit smaller number of start-stop cycles due to the flexibilization of the reference sites, so that the number of cycles can be reduced by up to 11%. And because both the number of operational violations and the number of start-stop cycles decreases the lifetime of the turbine, by flexibilizing the reference site, the technical aging of the inflexible units could be slowed down. This is an additional benefit. So to sum up the market simulation results, we have seen in the day ahead simulations that we have only a slightly higher demand in short-term flexibility in the market simulation. And the main driver for higher flexibility demands are especially volatile generation plants in the Nordics itself. Additional benefit was that the flexibilization of some units in the Nordics can slow down the technical aging of the inflexible units. I would like to go on to our second simulations and investigation program, where we did time domain simulations, where especially we looked at the frequency stability, and the scope of these simulations was inertia and frequency containment reserve. So in these simulations we want to answer the question, what advantages do flexible hydraulic power plants offer in terms of frequency stability? So therefore we determine future flexibility requirements for hydraulic power plants with regard to the frequency stability. In the framework of the Hydroflex project, we improved the Nordic grid model and the detailed modeling of the hydropower plants in the Nordics. Furthermore, within the framework of this project, we further developed an existing software model for the simulation of frequency stability and dynamic simulations and detailed analysis of reference cases. So now I would like to go on and see what future flexibility requirements for hydraulic power plants with regard to the frequency stability we determined in our work. Now I would like to show the investigation program for our frequency stability investigations, and here we used a Nordic grid model based on the TY-NDP 2030, where we used standard dynamic models and parameters for generation and load technologies, and detailed governor and turbine models for the Hydroflex reference sites. We also assumed no auxiliary services by HVDC and RES connected via power electronics to get the worst case conditions in terms of inertia and FCR provision. We looked at two different scenarios, one with the today's power plant park and one with the future scenario, and where we substituted the nuclear power plants by wind power plants. We set the FCR to the sum of the FCRN and FCRD to about 2 gigawatts. And the fault we considered is an outage of 3 power plants with a total generation deficit of approximately 1,500 megawatts for the given initial condition. And what we suggest now is that this fault shouldn't endanger the frequency stability with the given FCR. So now I would like to show the results from this simulation, and therefore you see on the right side the frequency trajectory of the reference sites. The status quo is the solid line and the future scenario is the dashed line. And what we can see here is that there are only small differences in the frequency nadir, and that the FCR is well dimensioned for outages of 1.5 gigawatt. Furthermore, we see that that hydraulic power plants in terms of inertia and FCR are mostly supported for the frequency stability. So we see that the technical capabilities of hydropower plants are very important to maintain the frequency stability today and in the future. So hydropower plants are essential to support the Nordic power system with lower inertia by their rotating mass, and auxiliary services like FCR by highly flexible controllers and turbines. To sum the time domain simulations up, the hydropower plants support the Nordic power system with a lower inertia rate by inertia and the provision of FCR, and the hydropower plants in the Nordics could provide flexibility in terms of inertia and FCR also for interconnected power systems as the Central European power system. That's it from my side. Thank you for your attention, and I'm happy to hear some questions.
Any questions?
Thank you for your presentation. I was thinking we quite often hear, you know, the one question is in installing more power in power plants, of course, but the question is how to get it out to the consumers, and then you come to the question of congestion and bottlenecks in the transmission system, which are notoriously hard to sort of overcome. How do you think that they will affect your scenarios, or are they taken into account in the simulations?
So I've heard this question also in our last workshop in the Hydroflex project. What I need to mention here is that we looked at market simulations without taking into account any grid assumptions and frequency stability simulations. So what we didn't analyze is what effects do we have with redispatch or other grid-related bottlenecks, and how hydropower can help there also, could help there as well. And what we've seen in the last workshops was that hydropower is also a flexibility provider to solve these grid-related problems in the future. But within our work, we didn't focus on this one.
Thanks.
Thank you. Hello, thank you very much for your nice presentation and valuable work. I have a question about the flexible case. You show two different scenarios, one without flexibility and one with flexibility. Which kind of flexibility did you consider? So was it a variable speed, for instance, or did you consider very, let's say, broad scenarios for technologies in hydropower that can add the flexibility?
What we considered, and I can go back to this, I think you mean this slide.
Yeah, correct.
When we flexibilized the units, we said that they don't have any minimum uptime and minimum downtime. So when you see what Ole said in the beginning, when we want to reach 30 start-stop cycles, they cannot have any minimum up and down time where they need to rest, because they need to start and stop more than one time in an hour, and therefore we put the minimum up and down time to 0 hours, and so that they can operate all the time if they want in both so they can change more frequently than the inflexible plants.
Okay, thank you.
You're welcome.
Okay.
Hello. Have you considered the market or the consumer flexibility in some way?
No, actually, we only looked at static loads in our simulations and didn't consider any decentralized, flexible energy resources in this model.
Okay. And have you been considering the hydrogen scenario?
No, not as well, because we are deriving the scenarios a little bit from the TIRA NDP scenarios, and they have not considered these ones when we started the project.
Okay, thank you.
Okay.
Okay.
No more questions? Thank you, Peter. Thanks a lot. Well done.
You're welcome.